Our next presentation came about because I thought it would be very valuable. We hear a lot about ABI. Right? We all know about Tim and his greatness. But a lot of that is from the science end. And there's a lot of instrument aspects that have to be dealt with ABI that we don't normally hear about. And of course, we have expertise of the great Paul Menzel regarding the working with current goals and how that works. And so, again, looking at inviting them to give presentations, I was thinking that it would be very valuable to look at the decisions made regarding ABI and the instrument characteristics, not just the science, and then look at that, how it compares to current and previous goals. And then I was in a room with these two, and we were in Wayne's room, and they started talking about, you know, this versus that, and I thought, you know, this could be really fun. And that was the other requirement I was looking for today, some fun talks. So hopefully we're going to see a great fun talk that is educational and inspiring, and will take us from the past into the future. And here is a little thing here if you want to use pointer. Or you can...
I'm not authorized to use the pointer.
And there's another mic here, Paul, if you want, or you guys push each other out of the way.
So you can see in Paul's logo there on GOES P, he doesn't have clouds on the earth, but we believe the clouds in GOES are in our logo. So. But your GOES you can flip upside down and still read GOES. So.
Let me just say a word about the format here. Tim and I are kind of sort of go back and forth. I'm going to talk about more what the past or the current capabilities are. And we've characterized those very well before launch and after launch. Tim is kind of stuck with talking about before launch. And it reminds me a little bit, as you go through a program, you start out in the very beginning overselling, sort of in the pants on fire mode. All right? And then as you get closer and closer to the reality, some of the things you thought were going to be possible actually are possible. So pants on fire wasn't true. And some of the things just are never going to happen. So we have some examples of that. The laws of physics don't change in spite of how much you want to oversell your program. If you don't buy a big enough mirror, you're stuck. So we're going to start out talking about some of the nice things, what kind of imagery, spectral bands, but then we're going to drift off to some of the nitty-gritty where physics still holds you by the belt.
So we hope that's fun enough.
Yeah, Tim is going to do most of the early stuff, and I'm going to go to the boring
It's
stuff.
the ghost of Christmas past and the ghost of Christmas future.
Special thanks to a whole bunch of people, especially everybody in this room because you're here. Paul talked about the past. That represents, as you can see, our building in 1967. I don't know if that's actually Paul walking on the corner there. It's just a rumor. Represented by current, Hurricane Katrina, the water vapor, and of course the future, the Lockheed Martin bus with the ABI in the GOES R.
How big is this thing?
It's like I think that the satellite itself is the small school bus type thing. I don't know if that's 22 meters or something once it gets unfurled. It's big. There you go, big.
So this is the history slide where we're going to spend a bit of time on it. Part of this history isn't even on here. If you, on December 6th, had a little nudge in your ear, it's because we were 46 years past the launch of ATS-1, the first geostationary satellite that Vern Simi talked Tomer Gould into putting on a very short notice. That was a spin scan, and we saw that the clouds moved around the Earth. The ATS, several of those led to SMSs. Several of those that finally led to the GOES, which were the operational spacecraft. All the other stuff was demonstrations, research, kind of things we don't do very much of anymore. So maybe Brad gets a chance. At any rate, 75 we launched GOES 1, and it was pretty much the spin scan, viz, IR window, so you had day-night viewing, and importantly, it was operational. And then Bill Smith showed up in 1976, I think, and brought his group here. And he had one main job was to work with Vern Simi on the the atmospheric sounder, VAS, the Visor Atmospheric Sounder, and we went from just a visible and 1 IR to a visible and 12 IRs. And we operated that in a mode where people who didn't want to never noticed it, and people who wanted to would look in the 10 minutes every half hour to catch Venetian blind sounding of the north part of the North Atlantic, of North America, and then 10 minutes later the southern part. So we had sounding.
And if I remember, when the weather got interesting, then they turned the soundings off.
That's right.
More images.
Right. To get rapid scan for Jim Purdom, Bill Smith had to give up his soundings. All right, so that went on for quite a while, and we got pretty excited about the soundings and the demonstration mode and the multispectral imaging. And then in 1994, something like about 4 years later, Joe Friday almost lost his job hanging on to the sounder. We got an operational sounder, and we went from a spin scan system to a 3-axis cable system. So here you're sampling in microseconds, and here you're sampling in milliseconds. And we're going to come back to that at the end of the talk. We still have time. Now we had an operational sounder with 18 IR, went from 12 to 18, and we had an imager with 5 bands, 1 vis, 4 IR. So things are looking great. We had some spatial resolution issues here. We also had some eclipse issues. The instrument would heat up too much. You had to turn it off. So then with 13, 14, and 15, the last 3 we launched, better navigation and calibration. Because this instrument now, because of the spinning, heats up by 50 degrees and cools down by those same 50 degrees. And the eclipse outages are gone because we did better sheltering of the instrument. And the water vapor and the CO2 channels that were jiggered on here at 8 kilometer got down to 4 kilometer. And we're still using 13 and 15 operationally, and 14 is a hot spare. So that's what we have now, and we sort of know what it is. And some of the things we promised way back then have become reality. And now Tim has to tell you what he thinks is going to happen.
First of all, I have to point out, before Goes I at the time was to be launched in 1988. So they hired me in 1987 to get ready for it. And I spent years waiting. So it was launched in 1994. Goes R was to be launched in 2008. And now I'm waiting again. Now currently launched, readiness October 2015. So Goes R will have the advanced baseline imager, 16 bands, better spatial resolution, faster coverage, and it will also have the geostationary lightning mapper on it as well. Yep, if you notice down at the bottom here, this is an artist's rendition of how much impact those measurements had on regional numerical models. At first, maybe they weren't regional models, so obviously the impact was small. Then maybe Goes 4 and 7, you had winds that got into the models. You know, some of the operational sounder data, radiances, a bit more, but obviously we're expecting big things with the products and data from the Goes R. You want me to? Yeah. Okay, so current Goes, of course, we have the imager upper left. We have the space measurements as well, at least on some of them. The solar X-ray imager, represented here upper right. The filter wheel sounder with 19 spectral bands is shown here, and what are called auxiliary services. That'd be search and rescue, data collection, etc. Then we go into the Goes R world. We become the advanced baseline imager. A little bit of an oxymoron. Is it advanced or is it baseline? Well, we improve our space weather characteristics with the aptly named SUBI instrument, to more spectral bands there as well. 1 minute imaging of the sun. We lost the sounder, but apparently we traded it for the geostationary lightning mapper. So total lightning, an optical scanner from geostationary with the coverage region shown there. And to confuse people, now we call it unique payload services, but still the direct broadcast, the GRB, etc.
What is that a picture of?
That picture is a boat having a bad day, and its signal was first picked up by Goes 11. And Goes will tell you that the beacon went off, but not know where it is. And and that's relayed, and the polar orbiters can listen, and then they can triangulate where it is. So, yeah, not the NOAA ship of state, that's right. And this is a data collection, a river gauge that the data is bounced off of the GOES to bring it back. So, okay, spectral bands. True or false, does GOES have more spectral bands? You all know this answer. Current GOES imager, 4 spectral bands in the IR. There's a little difference of the previous versions, but by and large those 4 spectral bands. If you look at the ABI spectral bands, now we go to 10 in the infrared. So you can see that we've traded 1 wide water vapor band for 3 more narrow ones. We've filled back in the 12 micron, in fact another cleaner window at 10.35, ozone sensitive band 8.5. 8.5, that's NOAA doing their job. Steve Ackerman wrote a memo to NOAA, 1988 I believe, please put an 8.5 on GOES. NOAA said yes, and it'll go operational in 2017 or later.
Time for another letter.
Or time for another letter. So, and with those new bands, of course, you can do more things. For example, if you want to look at upper level SO2 from today's imager, you can't. That's lower left. But there is a signature in a number of the bands. One of them, the 7.35, that was customized to be right on the middle of the absorption feature. And pictorially, the 5 bands from the current GOES versus the 16 bands. And so you can see, obviously, we have the 2 visible bands, 4 in the visible near IR, and go from 4 to 10 IR.
Forgetting something.
Yes, I am, Paul. So,
Sounder.
yeah. So
We had a lot more spectral bands in the sounder and the imager, didn't we?
that's right. So we'll call that one a tie. So we got 16 bands, you got 4, you got the sounder, but we have some of those same bands on the ABI. So okay. So there we go. Yeah. Yes and no.
Can you do sounding with ABI?
We can do them just as well as we do today.
Hands on fire?
Just a little bit because the temperature component. But mostly we use the water vapor to change our temperature moisture profiles. Of course, a step no better than we did in 1979 might not be the most positive mistake. So we'll give you
a good guess. You can
yeah,
make it a little bit better.
That's right, a little bit better for the moisture because of these 3 water vapor bands.
Right.
So that's a pretty poor man's.
You're a good man.
Number of detectors. Okay, so as you know, current imager, 2 detectors flipping back and forth. ABI and IR, that'll be 250 detectors. So you add that all up. Total detectors in use at any time, of course the redundant ones, were 5,000 detectors for GOES hours. So take that.
Okay. That's a lot of detectors. Good luck.
Yeah. Oops, bring me back 2 detectors. Coverage. I'd argue GOES has a simpler and a faster scan pattern. So if you look in 30 minutes, if you're in this regular mode right now with today's imager, you'll get 1 northern hemi, 3 CONUS images. But with the ABI, you'll get 2 full disk images, plus 6 CONUS images, plus 60 mesoscale, 1,000 by thousands in that same amount of time.
That's pretty good.
Yeah, 5 disks. Current GOES, as you know, we have outages due to a number of things, housekeeping, stray light, maneuvers, etc. Current series, that's on the order of, let's say, 300 hours per year. We'll drastically improve that, on the order of 50 hours outages per year with the improved spacecraft, etc. So then you can actually see Hurricane Ivan making landfall as opposed to what we have today. Because apparently the weather didn't stop. Here's a scan pattern. As you know, current GOES, we do full disk every 3 hours, northern hemisphere extended, southern hemisphere, this little calibration stripe. As opposed with ABI, full disk every 15 minutes, plus a conus every 5 minutes, plus these 1,000 by 1,000, one spot every 30 seconds, more likely 2 spots every 1 minute. So you'll be able to take imagery like this, although improved because it'll be finer spatial resolution, in this case in the north-south. This is some special one that data from GOES 14. We'll be able to get that all the time with ABI.
For that little box, how much in advance do you have to tell people where you want that box?
Right now, we have to tell operators 2 hours ahead of time. I think it's to be determined how, I think we'll be able to shorten that, but we'll have to find out how much.
That's pretty good. We used to have to schedule a day in advance in the old days.
Yeah.
We were a lot smarter than we are.
Yeah, we need all the time we can get. Yeah, that's right, yeah. Okay, coverage, simpler, faster panorama, and with less outages. Spatial resolution, in general, GOES is a factor of 4 improvement, 2 in the north-south, 2 in the east-west over the imager. So, for example, in this case, this is an old GOES 10 one. If you look at the fog there, lower right, and you can start to, this was simulated with the MODIS data degraded to expected ABI performance. So you can see 2 things that improve noise and also improve spatial resolution, which is also shown here. Paul's job is to find the fires in that lower left there. Hopefully we don't have to be quite as smart with GOES since we'll have a hotter saturation temperature for the 4 micron, and plus, of course, we'll get those images more frequent as well. So that's pretty good. So in summary, don't worry, we're not done. Again, if you look at the middle, the last 2 columns, basically goes 13, 15 have the 4 bands and the IR and the 1 visible, and we go to 16 with as far as fine as a ½ kilometer band in the visible. So again, spatial resolution's improved, but we don't have the oversampling because we're going to remap it to a fixed grid format. So if you look at all the pixels today from a GOES imager, you see that oblong Earth. We've made the Earth a sphere again by remapping the data before we send it out. So who could be against that?
Nobody.
Actually, it's Paul's idea, so he shouldn't be against that.
Okay. Tim, I got one critical question here. On ABI, how big is your scan mirror?
I actually don't 28 centimeters.
It's the same as my scan mirror.
Okay, great.
So, all right.
That's
So
a tie.
one of the things, scan mirror is going to have to obey the laws of physics. So the scan mirror did not increase in size. So the question you have is, how far away is the energy coming in to your 2 kilometer or 4 kilometer field of view, depending on whether your current goes or future goes? Well, you still have diffraction. Rayleigh's dead, but diffraction's still here. And pretty much with a 30 centimeter mirror, you can do visible at 1 kilometer resolution, which means that about 84% of your energy is coming from a 1 kilometer box in the visible. But beware in the IR. In the IR, this always goes with wavelength. What you're trying to do is capture most of your energy from the central maximum. Then you have these secondary and so on maxima, if you remember your diffraction theory from way back when. And here we're doing a circular aperture. So if you have a 30 centimeter aperture, you can calculate what your diffraction is. All right, so Harry Montgomery, my good bud from way back when, he did this calculation where he tried to figure out how big does the hole have to be over the ocean in a cloud of temperature varying here, 220, 260, 280, for you to get a sea surface temperature that's correct. So let's say you want to be within 1 degree of the correct sea surface temperature. Your hole in that cloud has to be, for 220, has to be 220 degree cloud. The hole has to be 15 kilometers in radius. Or another way of saying that is, if you want to be within 1 degree of your sea surface temperature, you have to be 15 kilometers away from something that's non-sea surface, like a cloud or land or whatever. So we may have 2 kilometer or 4 kilometer resolution, but we could get messed up by stuff that's a lot further away. If you bought a bigger mirror like the Europeans, Tim, they have a 50-centimeter mirror.
They use a euro, though, Paul.
This would be a much better picture. So this picture hasn't changed. The other thing, though, is electronics has changed. If you had a scene and you had a detector that was responding with a top hat, going over a scene that looks like a top hat, you would get a perfect response where as you gradually slide over, you would go to the peak at the instant when they match up. You're going from -1 to 1, if -1 is 0 really, and 1 is 1. So that would be your perfect response. But that would mean you're taking instantaneous measurements. And these detectors, they have to collect the photons, and then they have to be scraped off, and then they have to collect again, they have to be scraped off. This is done with electronics, and in the current goes, it takes a while for this thing to ramp up. So that your sample, which should have been one sample right here, ends up being spread out over 5. All right, so you find out that your encircled energy or your squared energy is coming from a lot more than just this top hat. It's coming from around here. It takes you quite a while to ramp up, and you never really ramp up the full output. All right, so this is what the current goes looks like. Perfect response to a step function, then the output. And it's spread out so that you have it spread out over 5 signals. This is a summary now of those 5 signals that are spread out. In the current goes, you have the fractional energy and the square sided length. The longest wavelengths are your most challenging because of diffraction. You find that you get to 84% of the signal, that primary maximum in the diffraction. It takes you about 6.9 kilometers square. So that's really your effective resolution on the current goes. Even though we say 4 kilometers, you better talk about a 7-kilometer instrument. Because of better electronics and longer sampling, here with the current goes, we take 180 microseconds, and here we take about, what did we decide, 25 times longer? Yeah. So because of the longer sampling and better electronics, but still being messed up by diffraction, we effectively, for the 13.5 micron, have a 3.5 field of view. So it's twice as good. So when we said we went from 4 to 2, we did get twice as good, but we should have said we're going from 7 to roughly 3.5.
Of course, when we say we have 2, we all have an asterisk and say, well, that's at the sub point.
That's right. Yeah, there's also that stuff. But this is at some point. If you're looking for something with a smaller footprint than 7 kilometers, you're not going to really see it. All right, so the fire people are aware of this. Chris Schmidt's been fighting this all along. But this is a good story, though. 84% of your energy. But for, this other 16%, if it's totally different temperature, that really messes you up. All right.
Could you explain once more how does the time translate into space?
Well, if you're tramping along here, if you're going very fast, you have fewer opportunities for the sampling to be on top of it. So if you're sampling 5 times slower, you have a better opportunity to ramp up.
Sampling occurs along the scan line.
That's right. You're moving along, not at the breakneck speed of a spin scan. I got 2 minutes, so I got to move on. Circled energy, bottom line is yes, it's better. All right, signal to noise, yes. Signal to noise continually fights its detectivity curve. These are Mercat Telluride detectors, functional wavelength. This thing drops off like a cast iron safe when it gets to about 11 microns. All right? The Gifts and all those guys, they wanted to live out here, and they got a lot of bad news about signal to noise. Fortunately, as you get to longer wavelengths, you're seeing only the upper atmosphere, so you can do some averaging. But ABI wasn't brave enough. They went out to about 13.5 and took some significant hits of noise. You can move this thing up and down a little bit by changing the doping. So you can improve it out here, but you mess it up here. The sea surface temperature boys always win that battle, so your 11 micron has to have the best signal to noise. So here it is again. So these are the kinds of NEDRs. This is what you're actually getting, radiance noise. And then depending on what temperature your scene is, you turn it into a NE delta T, a temperature noise. So here's a comparison of Tim. He's trying to be the honest broker here. He's going to be better than a tenth of a degree. I'm living up here more in a quarter of a degree world right now. So that's nice. He got better spatial resolution, and he got better signal to noise. 2 attaboys. All right.
First of all, I'd like to point out it doesn't have anything to do with bravery in the 13.3 ABI, because we have this advanced baseline sound to remember. And we're going to have all this good CO2 sitting right next door.
Talk to Hank about that. All right. So one of the things I'll say for Tim also is these are pre-launch estimates. He doesn't have post-launch. Our pre-launch was always pessimistic on the past satellites. We did a lot better in reality. All right, so that's good. Bit depth. Bit depth is important because you got to take the maximum radiance and slice it into however many bits you can allow. We lived in the 10-bit world with the current goes, and so we had a lot of truncation error. All right, so truncation error, in addition to signal to noise, is an issue. Truncation error for cold scenes is bigger than for warm scenes because of the slope of the plank. For Planck and Rayleigh, they're dead, but they're still hanging around. And so you have this truncation error. For a cold scene, you look at the 4 micron, holy moly, you're truncating it in 2-degree boxes. If you want to figure ice from water with 2-degree boxes, good luck. All right, so this is with the 10-bit world on them. All right, Tim spent a lot of money, and he got 12 to 14 bits, and he's got himself up to ½ a degree truncation error now at 240 degrees. He had to get a better temperature. Actually, if it were 230 degrees, Tim would be sitting at a degree. So you're getting closer. But part of the problem with the 4 micron is it's shooting off like a nonlinear fashion, something like temperature to the 12th power. So if you want to get to saturations at 410 degrees for those fires, you're going to pay the price. We only went to 335. We were a bit more sane about this, but you fire guys, you want out. At any rate, more bits, better instrument. I can't argue. Tim, you did a good job,
well,
but you forgot the sounder.
To be honest, though, the bit depth is actually selectable on orbit. So even though this is our plan right now, you can always worry that at some point you get up and say, oh, this
You can select 16 bits?
oh,
that's great.
Yeah, it only goes one way.
So, all right.
Okay, we better. Okay, so, you know, current goes, applying a lot of good critical information, fires, fogs, winds, etc. ABI is going to continue that. Know we're all about continuity, improved spatial, spectral, temporal. We're going to have some new products that the new bands allow, building on previous experience. And just as Brad, we're building this geo constellation with ABI like imagers, Japan, Korea, Europe, United States. So again, we can start covering we haven't talked much about calibration, but ABI will have an on-orbit visible calibrator, which is something that we don't have with the current instrument. We've got web pages, but be careful about this goes our web page, so apparently not anybody on there. So, anyways, and lots of links, and I think we're done there.
Are you going to give up this slide?
So yeah, questions for these 2 experts? Yeah.
When is the Japanese ABI going to launch?
2014, the year before.
Yep, and I believe there's some memorandum of understanding going around for us to try to make sure we get that data either before it's officially released or maybe try to get some of the stuff before we map.
So the first ABI is supposed to be over Japan.
Correct. But don't worry, they paid less.
And where was the first goes? Is that over Japan too? I think Paul wins that one, right?
Yeah. First goes went over the U.S.
Yeah. Other questions? So I have another question while you can answer as I bring up Nadia's talk. So you have an improvement in the instrument in general. I think you've agreed with that. But of course, with the instrument goes with decision-making processes of when to turn them on, when to turn them off, how to distribute the data. Has NOAA significantly gotten much better as much as the instruments?
You mean better as far as more entrenched?
I'm going to let you define the word better.
We have more of a process nowadays. So yeah, no, back in the old days, you could call up Paul and say, boy, we'd really like to have this schedule run experimentally, and you would call up, forget the guy,
Davis.
yeah, anyways, it would get done. And nowadays, you know, say, well, we'd like to change the name of this product with what the whole community does. Yeah, no, we can't. So that's how I answer.
So Paul wins?
Yeah, Paul wins. That was a lot more fun in the old days, yes.
One of the things that Bill Tim sort of runs it, but
But at a distance.
Explain.